Alrighty, so I got recording going there. And just in case, I also have my other program that says, I need to start recording. Just in case, because I have had situations where one hasn't worked. All right, so chapter 11, the last thing that I really want to cover here, and I covered all these calculation stuff yesterday, and so we're going to continue here. And we have something called a phase diagram. And when we're doing these calculations, we really, if we really look at it, we're doing phase calculations. But here's how it works. You have, if we look at water, and water is a very interesting substance. From a sciencey sort of standpoint, it really is interesting. And you have solid, liquid, and gas. Okay. Now, you may say to yourself, well, of course, I got solid water. It's called ice, right? Water is wet. One of those kind of things, right? Well, you look at it, and first off, if you look at this very carefully, you will see that solid goes to liquid, and then liquid goes to gas. And so you can take a pot, and I love using these common examples. You have a pot of, you have these ice cubes, and you put it on the, my dog's going crazy for some reason. Can y'all hear the dog? Justin, can you hear the dog? I'm sorry. The first thing you do with a dog when you get them is tell them to shut up, right? So anyway. I can't think when he barks like that. All right. Gus, safe spot. Does anybody want a dog? Yeah, he's free. You sure, Crystal? So I have to ask. Because I'm a sciencey sort of curious guy. Crystal, why are you wearing a face shield? Are you like at work?
I am at work.
Are you around like sick people?
I'm working with COVIDs.
Wow. Well, you know what? I'll tell y'all something. They don't let me out much. And fortunately, that means I'm relatively safe, so I've heard. Since I don't get out much, that's what I've heard. But I keep telling my wife, I'm like, you know what? Every time she goes off to like Harris Tweeter or Harris Teeter, we call it Harry Tweeter. Every time she goes off, I'm like, please wear your mask. Please don't kill me, right? I can't be killed because I've got to enter grades in next week. You know what I'm saying? Let me tell you something. The last thing you want is for your professor to die. It causes all sorts of problems. It really does. I actually had that happen where my professor, he actually died like 2 days after entering the grades. He had a heart attack. He was like 40. And I was like, holy crap, what happened to Professor blah, blah, blah? But anyway, so you got to wear a mask, huh? Dang. All right, let's take a look at this phase diagram. All right, let's get back to this. All right, so we look at this phase diagram, and this is water. How do I know this is water? Oh, I'll tell you how. Check this out. Do you see this right here? It leans back. most things in this world, in the world that we live in, actually look like this. Most things actually look like that. And you may say to yourself, well, so what? Well, this actually has a big, big impact on the way the world works. Okay. And so if you look at this as you go from solid liquid to gas versus solid liquid to gas for most things. All right, this is the part where chemistry gets really interesting. You got to look at it and you got to say, what does that really mean? Well, this has exciting implications. First off, ice floats. And you may say to yourself, well, of course ice floats. That's what I see all the time. But you know what? This is actually quite unusual. Because you see, if ice did not float and it behaved like these guys over here, what would happen to the Earth? Well, as soon as ice formed, it would sink. It would go down to the bottom. That's what would happen. So if you're floating around in the ocean, ice would sink to the bottom. This is not a good thing. If ice actually did not float and it actually sank to the bottom, it would sit to the bottom. What would that mean? It would mean that you would not have insulation at the top and your oceans would freeze. All our oceans would be frozen solid by now. Okay, so ice floating on the top actually prevents heat from coming out. Okay, so bottom line is, if it weren't for the fact that ice actually floats, we would be in serious trouble as a planet. Well, it's okay. It floats, so it actually insulates what we have going on there. Now, a more fun fact. Here's a fun fact. All right. If I was face to face with y'all, we would do fun facts all the time, but we're not. But let me show you something here. You see how this leans back? Do you see that? I don't know if anybody here is a skater. I actually used to be a competitive pair skater. Imagine that. Let me put on my pink glasses again, okay? I used to be a competitive pair skater. And how does ice skating go? It goes like this. Okay, you have a blade. And of course, you got the foot on top of it and all that. Okay, but there's a blade. All right, and if you look at it from a sideways, head-on sort of look, it looks like that. Okay, so I'm looking from this direction. Now let's take a look at our phase diagram up here. This is why we do these things. Okay, we look at this phase diagram and we see 1 ATM. Okay, so as you're pushing on the surface of the ice with the blade, what's going on? Remember, I keep saying that because that's really what science is all about. You have to ask yourself, what's going on? And so what's going on here? Physics guy, Justin, what do you think? What's going on here? Are we applying a lot of force?
Just gravity times your mass.
Gravity times your mass. And what do we have here? We have a very thin. So what's happening to all that force? It's actually getting applied to a very small area, right?
Mm-hmm.
Yeah. And so the actual force, the pressure is much higher than an atmosphere. So if you're here As a matter of fact, let me change colors. Let me change it to green. Let's say you're here. You're solid ice, right? You're gliding over it with your blade. What are you now? If you're here. Well, you've gone from the solid to the liquid phase. We got to be able to read these graphs. You've gone from solid to liquid. So what do we have here? What do we have right underneath that blade? What do you think? We got liquid, right? For that moment that the blade is going over the ice, it actually is liquid. And guess what? Liquid is a great lubricant. And so as you're sliding across the ice, for a moment, I don't know if anybody's ever been ice skating, but you know, for that moment underneath your blade, it's actually liquid. And then as you go past, guess what happens? Well, first off, it would help if I could do my colors, but guess what happens? It turns back into solid, because as you are going across the ice, you're liquid. And at the moment you go back, not across, it's a solid again. So the only reason why ice skating even works at all, the only reason why it even works at all is because, well, it's got a backwards facing liquid solid line. That's the only reason why it works at all. Because ice on steel has a different friction coefficient, has a different coefficient of friction than on ice on water, and different than, say, steel on water. They have different coefficients of friction. Matter of fact, the friction coefficient is almost zero. So you can see these guys, you know, they're gliding across the ice and they're going really fast, and that's because, well, it's turning the water when it's underneath. And then it's turning the solid when they come off of it. So from a practical standpoint, and I love pointing out this example because if you Google me, should you be able to figure out who I am online, you'll actually see some pair skating going on there, you know, me and my partner. So, and that's how it works. Okay, that's how it works. Now, let's take a look at this thing again. All right, I'm going to draw it again. All right, so we have solid, liquid, gas. Okay, now, when you're looking at this sort of chart, how is the easiest way to look at this? Okay, this is pressure. The easiest way is to remember, what order do things happen as far as, you know, melting ice? What happens to ice? Well, let's see, you start out with solid. Yeah, you put it on the stove, it turns into a liquid, then it becomes a gas, right? Common everyday experience. Which way does this graph go? Which way does it go? It goes solid, liquid, gas. So if you are just faced with, and this is, you know, one of these test sort of things, right? You have this in front of you. How do you label it? How do you label this thing? Well, you look at this and you go, you know what? What do I know? I know that solid ice goes to liquid water, which goes to steam. All right. I know this because I'm a human being and I've lived in this world for however many years. Okay. So what are you going to do here? Well, I know this is degrees Celsius down or Kelvin. Doesn't matter, right? Remember what I told y'all about Kelvin? You be careful. And we have pressure. Things depend on pressure, right? So how would you label this? Well, you work from left to right. You say, oh, you know what? Things are cold, they're solid. Things get hot, it's a liquid. Things get even hotter, it's a gas. All right? And so what does this line right here represent? What does that mean? Okay, we got to be able to look at these graphs and be able to interpret them, all right? All right, so what does it mean? Well, if you think about it, what do we call going from solid to liquid? Let me think about this for a second here. Oh, I know what it's called. It's called melting. All right. And if you go back the other way, it's called what? It's called freezing. So what would we call going from, say, liquid to gas? I don't know. Let me think about it for a second. I think I'd call it boiling or vaporization. Or vaping. Yeah, vaping. Yeah, we call it, well, look, you have to be able to look at these graphs and be able to say, what is it that I'm looking at, okay? Now, since this is 1 ATM here, okay, these spots where we cross here, since it's at 1 ATM, we actually give them special names. What do we call when we're melting at 1 ATM? We call it the normal melting point. What do we call when we're vaporizing at 1 atmosphere? Yeah, we call that the normal boiling point. Now, why do we call it normal? Because, well, it's at 1 atmosphere. This is the temperature that we're at and the pressure that we're at. All right, that's why we call it normal, because, well, if you put a pot of spaghetti on the stove, what does it boil at? It boils at 212 degrees or 100 degrees Celsius. 212 Fahrenheit or 100 degrees Celsius. We call it normal because, well, it's a normal pressure. All right, now, I want to show you something here. All right, we're going to look at the same one right here, but let's say that we go up to Mount Everest. Go up to the top, or maybe even just out to the mountains somewhere. Look what happens. This might be 100 degrees Celsius here. This is a lot less than 100 degrees Celsius. You see that? If we go down in the pressure, I'm just looking at the graph. Okay, and we go down to the pressure, maybe this is 75 degrees Celsius, thereabouts. So as you go up in atmosphere, so here is lesson number 1, besides looking at this graph here, here's the conclusion. As you go higher, what happens to the pressure? Pressure goes down. What's the other thing that happens? Boiling point goes down. Matter of fact, there's something called freeze drying. I don't know if you ever heard of something called freeze drying, but the whole idea of freeze drying is that if you pull a hard enough vacuum on something, you can actually get it to boil at room temperature. And if you can get it to boil at room temperature, you don't cook whatever it is that you're trying to freeze dry. Think about it. If you want to actually, evaporate off the water off of something and you did it at room temperature and at atmospheric pressure, well, you'd end up cooking whatever it is that you have. So if you can pull a vacuum on it, well, guess what? Now you're down into here. And guess what happens? You end up evaporating off the water. In other words, that's what boiling really is. But you do it at room temperature if you pull a hard enough vacuum on it. And so you can do things like take coffee. And this is, by the way, for many, many years, people try to figure out how to turn coffee into instant coffee. You ever seen instant coffee? It's terrible stuff, but people want to know how to make, coffee crystals. And the way you do it is you pull a good vacuum on it. You can pull off the water. Why can you pull off the water? Because you're down over here. All right, that's the reason why you can do it. You can pull off the water because you're over there. You're not hot anymore. It's boiling, but it's definitely not hot anymore. So you don't end up with this like tar down on the bottom. Okay, now, all right, so let me show you. I'm going to draw the same picture again because there's a lot of information here. Okay, there it is again. Solid, liquid, gas. Okay, we got degrees Celsius or Kelvin, and we have pressure. All right, so by the way, you see that point right there? You see that thing right there? All right, it's got 3 lines coming together. It's got 3 lines. We got line 1, we got line 2, we got line 3. Guess what it's called? Triple point. How can you find a triple point? You look for 3 lines coming together. Literally. Triple, 3, triple point. Got 3 lines coming together. Okay, there's 1 line, there's 2 lines, there's 3. That's called a triple point. All right, so at the triple point, you have all 3 phases at the same time. You got solids, you got liquid, you have gas, all at the same time. All right, and you may say to yourself, well, that's interesting. But, you think about it. What have you actually seen? How about ice cubes and sweet tea? I love sweet tea, but how many phases do you see there? I see solid ice and liquid water. You got 2 phases. You got, you got ice cubes and you got water. I mean, that's basically what sweet tea is, right? It's just water with a lot of sugar in it. And so, you have 2 phases. But what do we see here at the triple point? We have 3 phases at equilibrium. All right, we see them at equilibrium, which means we have to take account of the vapor, water vapor, above the sweet tea. And by the way, it's got to be a sealed up container too. All right, and triple phase is unique. Unique in the sense of there is only 1 temperature, 1 pressure that's going to get you to triple phase. All right, there's just 1. Now, what do we need to do? What do we need to do is, there it is. I found it. All right. Where is it? It's right there. It's where the 3 lines come together. There's your triple point. All right. Now, what does that temperature have? What's the pressure? You know what? You look it up in a table. All right. And I forget what it is, but it's pretty cold and it's pretty low pressure. I don't remember what it is off the top of my head. Nobody cares. But, hey, we have to be able to look at a graph potentially, right? And say, put our finger on it. Say, where's the triple point? There it is. It's right there. Okay, that's what we need to be able to do, is we need to be able to put up where the triple point is. Now, there is another point that I want to show you here. Right here. Do you see that? I just circled it. That is not because I ran out of room on the graph. All right, and it kind of looks that way. I ran out of room, but actually, it has its own special name. It's called the critical point. It's called the critical point. All right, and it is where going out in this direction, not gas, not liquid. Okay, so you can't really tell them apart. It's kind of a gas and it's kind of a liquid. But beyond that point, you really can't tell them apart from a traditional, hey, I got some liquid, got to put it in the cup, or I got a gas that fills up something. Okay, pretty important. If you ever go off into industry, one of the common things to use is CO2 at the critical point, carbon dioxide, because it makes a great cleaner. It acts like a liquid, it acts like a gas, and it goes away. And that's what matters. Okay, so beyond this point, we call that the critical point. Now, once again, it's something you look up. But what am I looking for? What am I looking for? So right there is called the critical point. Right over here is the triple point. And going from this to this is melting, and going this way is freezing. Okay, going from here to there is vaporization or boiling, and going from here to there is condensing. And oh, by the way, you can go directly from solid to gas. Okay, so you go from solid to gas, that's easy peasy. That's down in here, and that is called sublimation, which is something that carbon dioxide does. You ever heard of dry ice? Well, that's what dry ice does. It goes from solid to gas directly. Okay, and that's called sublimation. Now, water doesn't do that at ordinary temperatures, but it can. If you reduce the pressure enough, you can go directly from solid to gas without, having any liquid involved. And it does happen. So you call that sublimation, and then you go back in the other direction. That is called deposition. Now, you have seen deposition, believe it or not. If you look, if you go out to your car, I'm going to draw a car. There's the car. Yeah, it looks more like a limo, but there's my car. All right. And so you go out in the morning, and what do you see? What do you see? You see ice on the windows, right? But you see ice, and it looks like this. It's like there's little fingers coming off of it. You ever seen that? Well, that actually didn't come directly from water. It actually deposited from the air, water vapor in the air. And it actually does get cold enough around here to do that. What do we call that? That's called frost. Now, what do we call it? Yeah, it's called frost. Well, guess what? It can be cold enough on your windshield that the very air vapor that's in the air, the water vapor that's in the air will actually deposit directly on the windshield. And we call that deposition. So you have seen deposition. Now, sublimation, unless you've seen dry ice, you generally don't notice it. But believe it or not, if you see snow actually will evaporate over time. It doesn't just melt. It can actually sublimate into water vapor directly from the solid ice, snow, into water vapor. So it can happen. It can happen. Matter of fact, that's what happens in Antarctica. To all that snow that, gets deposited over 10,000 years. Where does it go? It doesn't melt. It's not hot enough, but it does eventually evaporate. And that evaporation is sublimation. That's what's going on. All right. If that didn't happen, it would be 20 miles tall instead of 5 miles tall. All the ice in Antarctica. All right. Okay. So those are the things that we are looking for here in this graph. Okay. Where is the triple point? That's where the 3 lines come together. Triple means 3. Yeah. Where are we looking for the critical point? The critical point is right here. It's right there. There's the critical point. Okay. Do we need to be able to read a graph? Oh, you betcha. Let's say we have 0 degrees Celsius and we have 100 degrees Celsius. If you're asked, where's the triple point? Well, what do? You look for the pressure, 0.01 atmospheres, and you look down, right? Isn't that how you read a graph? There it is. Okay, so you need to be able to read a graph. So, if we're looking for whatever the triple point is, then we have to be able to look and see where do these things go together. Normal boiling point, normal freezing point. How do we find that? We look for 1 atmosphere. That's what we do. We look for 1 atmosphere and we look across, we look down, okay? 1 atmosphere, look across, look down, whatever that happens to be. Everything has a phase diagram. Everything has a phase diagram. What's the importance of a phase diagram is that you're able to look at it and say, okay, where's 1 atmosphere? Let me look across, look down, okay? That's what you have to be able to do. All right. So questions on phase diagrams. I've pretty much belabored it to no end. By the way, skip liquid crystals. They're interesting, but they're not that interesting. Matter of fact, if you have an LCD TV, and many of us do, if you look at the chapter, it's kind of interesting in that aspect. Okay, I know how LCD TVs work now. They take molecules and they orientate them, and light can go through in one direction and they can't go through the other. And if I was to describe liquid crystals, long, skinny, and stiff. All right, long, skinny, and stiff. That's how I describe liquid crystals, in the sense of they have to be long to be able to orientate. They have to be skinny to be able to line up with each other, and they have to be stiff to not flex around. All right, long, skinny, and stiff. There you go. Just like KMT. What's KMT? Small, fast, far apart. Right? We can describe these things in 3 words or less, I hope. Okay, so liquid crystals are long, skinny, and stiff. All right, and they have to be, otherwise it just doesn't work. All right, let me see if I missed anything here. Alrighty, let's see. Select the properties. We're not doing liquid crystals other than just what I just told you. All right, so why don't we go ahead and I think we're done with this chapter. And so we need to go ahead and finish up chapter 13, I think it is. Yep, we're going to skip chapter 12. Chapter 12, if you're going on to 152, you will get chapter 12 in 152. We're not going to do 152. All right, we're not going to do that chapter. So why don't we go ahead and take a short break? And so let's see, what do you think? Let's see, 10:40, 10:50. How about that? So we're going to take a break to 10:50. That'll give us 8 minutes. I don't know why I pick 8 minutes. It's a good number. All right, 10:50. Be right back. I say that